Good afternoon, everybody, and thanks to the organizer for having invited me here to give a talk for an update of nicer analysis of these two sources, J0030 and J0740, using a software called X-PSI, and that I will explain you about later on in the talk. As Bruno mentioned, my name is Serena Vinciguerra, and I'm a postdoc at the University of Amsterdam, and I'm currently working in the group of Watts. And one of the main goals of the group is indeed to analyze the data coming from NICER, which stands for Neutron Star Interior Composition Explorer, which is an X-ray telescope installed on the International Space Station. Okay, so this is a quick outline of my talk. So I'll start with an introduction about photon file modeling, which is the technique that we use to analyze this X-ray data, and about this software X-PSI. I will then go ahead and summarize the published results on J0030 and J0740. I won't have time to actually go into the update analysis of the already published data for J0030, but with an updated instrument response. But if you have questions about those, please just ask me at the end. And what I'm going to focus instead is what are the latest results using new data sets where further observation has been included. And so what are the preliminary results for J0030 and the results for J0740. And I will then conclude with just some remarks. Okay. So what we know about the neutron star is, of course, very limited, as everybody here know very well. And in particular, we don't really know what is in the core of a neutron star. And why does this matter? Maybe I'll.
Yeah, you can remove the mask. Sorry.
Yeah, that's actually. Okay. Why does it matter? Well, because looking at what is inside, understanding what is inside the core of a neutron star, we can actually understand all the behavior of matter at very high density and low temperature. And to try to understand this, actually, I think that the best tool that we have is actually to communicate with each other and have a feedback loop between observations and theory. And now I apologize for the very simplified picture, but suppose you are curious, then you say, okay, let's suppose that the neutron star core is composed by deconfined quarks. Then what you do, well, you probably do have to take other assumptions, but then with those you can understand particle interactions. And from there, you can go on and build an equation of states. And what is an equation of state? Well, I guess most of you know, given the talk of this morning already, but just to summarize, is a relation that links temperature, density, and pressure. And for the cold non-interacting neutron stars, which are the sources of NICER, this actually reduces in a function between pressure and density. Then you can actually use the relativistic structure equations to uniquely map one relation in the pressure density plot to a relation in the mass radius of neutron star. And then what happens is that you can then start to change your assumptions behind your initial hypothesized neutron star core. And what you end up with is having this population of relations in this mass radius plot. And the idea here is that what we want to do is to compare this expectation, these predictions, with observations. And so far, one of the most important observations that have been useful in terms of considering the equation of states is the observed maximum mass. And indeed, in the last decades, we have observed increasingly more massive neutron stars, and these have already excluded some of the theorized proposed equation of states. But looking towards the future, what we really want to is to end up measuring for different neutron stars, mass and radius. And ideally, this would end up mapping a very specific relation in the mass and radius. And from there, you will go backwards and infer what is the equation of state, and from there, what are the particles in the core of a neutron star. Of course, I mean, this is the ideal scenario, but we are trying to go to actually do this with measurements, X-ray measurements such as NICER. However, at the moment, the uncertainties are definitely not so small to just include one single equation of state, unfortunately. But this is substantially the idea behind what we're trying to do with NICER. And just be aware that there are going to be more talks about this tomorrow by Slavko and Cole, and also particularly focused on what we can learn in terms of equation of states on Thursday by Heb. But here forward, what I'm going to try to focus on is just measuring this part of the processor, the measurements of the mass and the radius of neutron stars. Okay, so the idea is the following. We have a neutron star, which is emitting some pulse emission due to a return current that heat up some specific parts of the neutron surface. And this thermal emission that is therefore emitted is actually picked up in the X-ray by the NICER telescope. Then the data goes through some screening, and then finally reaches us, and we can use Bayesian codes software to infer quantities such as mass, radius, and other parameters that go into the analysis, such as hotspots configuration, etc. The NICER focuses particularly on non-accreting Unista composer. And what we get from NICER is actually a type of data which is like this, and which represents the pole profile, hence the name pole profile modeling. And this is, it has on the y-axis instrument energy or channels. On the x-axis, it has a phase of a cycle in rotation. In terms of rotation of the neutron star, and the color axis represents the counts. So substantially, if you could just take one single row in this matrix, this would be a Likert for a very specific instrument band energy. Okay, and what do we do with that? How do we get to the mass and radius? Well, there are some relativistic effects that come into play and modify the emission that we actually get at the surface of the neutron star. At the detector. So here, and just to illustrate some of these effects that are relevant to us for measuring mass and radius. So here there are two cases where we have a surface where there is a single hotspot emitting. That's here. In this case, we have no gravity. In this case, we have gravity. And here you can see the light curve that this produces. And you can see that as soon as we turn on gravity, instead of having the light curve disappearing for a certain moment where the hotspot is behind, because of gravitational lensing, we can actually keep still seeing the hotspot even when it's behind the surface. And this is something that, of course, depends on parameters such as mass and radius, and therefore we are able to use this effect to actually measure mass and radius. And so this is also what X-PSI, this Bayesian software, does, on which I will focus the analysis on for this talk. And so what X-PSI does, it is able to predict what is going to be the emission from the surface of a neutron star, given a specific parameter vector, which includes specific values of all the parameters that we need, that is mass, radius, and other parameters describing the geometry of the hotspot, for example. And then it will tell us how the instrument NICER sees this particular emission. And in the end, what it will be able to do is providing us with a model which has the same structure as it has the data. And so something happened. Okay, this way. sorry. Okay, so again, this type of data that I showed you before. So we have again instrumental energy or channel on the x-axis, phase of the cycle of the neutron star on the x-axis. Sorry, that was the y before the instrumental energy. And the color axis, we have counts. And what we are trying to do using X-PSI, which is in terms also using sampler multiness with Bayesian analysis, is to find parameters that are able to produce models which very well match the data. And in this way, we are able to infer probability distributions, so posteriors, for all the parameters that goes into play, in particular mass, radius, etc. And we have them represented usually in 1D or 2D representation here in this column plots. Okay, so X-PSI to model to produce this model, X-PSI has specific type of model generator, if you want. And so we assume that there are two emitting hotspots, and we use circular patterns to generate these models that are then used to compare against data. And we actually can increase complexity of these models by breaking the symmetry. So going from this case to this case, for example, you can see, so this would be the two hotspots where they are antipodal to each other, and temperature and the size of the hotspot are the same for both of them. Here we break the symmetry for this model, so the hotspots are independent from each other. And then we go more and more complex models where we can add more of these circular patterns to create different geometry with double temperature or even mass in one part of the emission, creating the possibility of having shapes such as rings and arcs. And for what follows, there are two models that are interesting for us. These are the SCU, where we have two circular single temperature hotspots, and the X-PSI, where we have one circular hotspot single temperature, and the other hotspot composed by one single circular emitting single temperature emitting hotspot, but with masking circular pattern on top that allows again to create these arcs and rings patterns. And why is this important? Okay, well, imagine you have, we now meet someone from the year 3000, and they are trying to communicate with us. And imagine this person will tell us something like pretendus. Okay, so how do you understand what that means? So you can imagine that probably the language that they speak is derived by the language we are speaking today, but you have to make an assumption of which language that is. And if you assume that the original language is actually English, pretendus, you could think it is pretend. However, if the original language was instead Italian, that would actually mean I demand, pretendo. So that gives very different answer. And this is like the same type of translator is what we are doing playing with models here. So the idea is that we try different models, and we do get a bit of different answer. So this is where I think the theory inputs are very important, because the more we have constrained theoretical models, the easier it is for us to understand which of these models we should favor. And for what happens in this case, which is for the pulsar J0030, we have preferred a X-PSI case based on the evidence value. Okay, so I'm now going to go for a quick overview of the published results so far from the NICE collaboration. Let me just start saying, so here you can find like a series of papers concerning the publication of these two pulsar, J0030 and J0740. There are two independent teams which are analyzing the data with two independent codes. You are, of course, welcome and encouraged to look at both of them. However, hereafter, the numbers I'm reporting are really focusing on the analysis done using this X-PSI software, where the group has been led by the Amsterdam group, this analysis. Okay, so these two pulses are actually already, as you can see here, quite different. So first of all, we have J0030 is an isolated pulsar, while J0740 it is in a binary. And what does it mean? Well, it means that thanks to radio observation, we actually have some priors on important parameters such as inclination and mass. And this is really very important to us and for our analysis. And so what are the results we obtained so far? So the first published results were for J0030 that was published in 2019. And it was the first time that a mass was measured for an isolated pulsar. And the first time that we had 10% accuracy or precision on the measurement of mass and radius of the same pulsars. Last year, instead, there was a publication for J0740. And well, for this publication, we had the first detection for this particular pulsar of pulsation. And this was actually a very interesting detection measurement because in combination with this isolated pulsar, you can see that the two masses are quite different. So this has a strong implication on the equation of states. But I'm not going to talk further about the equation of states because again, there are going to be talks in the next days that will go deeper into this. And let me also just mention that these measurements here are actually coming from the joint analysis of NICER data and the average, pulse average data from XMM. Furthermore, well, what we have seen with this publication, it was the first time that we have been seeing patterns of the neutron star surface. And this pattern can be actually used to understand and constrain the magnetic field on neutron stars. And I mean, here, let me see if I can show the video again. Yeah, you can see, for example, particularly for J0030, that the geometry is very peculiar. And this is actually very different from the antipodal circular hotspot that you would have expected with a center dipole. Okay, now let me pass through our later findings. And let me start by introducing the new data set that we are looking at the moment. So again, we are looking at the same pulsar, the J0030 and J0740. These are on the top here. I reported the data that have been published so far with exposure time and the observational period concerning to that. And in here in purple, here I have the table with the new data set we are looking at the moment. So for W030, we have an updated data set built in a similar way compared to what was done previously, where the exposure time has reached 3 megaseconds. So that's great. And but we also have a new data set from both W030 and J0740, which is called 3C50. This is made in a different way. There are stronger filter on top of to actually end up having this particular data sets to allow to have the background more under control. So we are also talking about cleaner data compared to the classic way of producing data sets so far. But one of the stronger news of what we are seeing now is that we now have constraint coming for the NICER background that we didn't have before. So we now have space weather constraints for these two data sets. So the new one for J0030 and the old one of J0740. This puts a lower limit on the background of NICER. And we actually have background estimates for these three new data sets, 3C50. So in that case, we can actually have lower and upper limit for the background. Okay, so let me tell you what's the idea here, why is it important? Well, let me just start saying, well, the background for us, and what do I mean with background? That is everything that is not coming from the thermal emission from the two hotspots on the surface of the neutron star. And that is very important for us because actually we produce a likelihood that in the end analyzes the data and drives the entire analysis, we marginalize over this background. So this is really crucial. Oh, I'll try to speed up a bit. Okay. Usually what we get from NICER is, so if you just look at the phase average here, we have a likelihood, and there is always this constant part here, and an unpulsed component. And this actually can have two origin, and you can imagine that hotspot origin, so it can come from geometry and geometry of the system, or the compactness, or non-hotspot geometry. And this is an important degeneracy that is in our analysis. So now going back to J0030. So what was found again is that in Riley et al. And also Miller et al. Well, okay, just focusing on Riley et al. It was we had like X-PSI was the model that fit well the data. And the radius was about 13 kilometer and 1.3 solar mass for this isolated neutron star. And so what do we see now? If we look instead at SU, so this is a much more computationally cheap model. So this is for exploratory runs. And if we look at the likelihood surface, where here we have two geometry parameters, those are apparently more constrained than parameters such as mass and radius. And we see that there are a really prominent structure if we don't put any constraint on the background. So we normally integrate and do our analysis. We see these peaks here. And these come up from both PC50 and Charlie dataset to be consistent with what was published in Riley et al. So we have this major peak here coming from this geometry, and this again is consistent with what published. And there is also another structure there that in this case does only pop up as a secondary peak, but is still below the other one. Then what we can do for 3C50 is actually imposing some background constraints. So going from the gray to this red and blue area here. And this makes dump completely some of the mode that we saw before. And now we only have very different geometry popping up. And in particular, in this case, these are the type of geometry here. So it's really very different. So this is really important for us to have background constraint. This is like, there is a catch here for this particular model. First of all, the model is not our preferred model. And second of all, we did not include the contribution of a star, which is actually in the field of view. So we will have to redo this analysis with that part included. But this was a good exercise to understand how sensitive we are to background. And so in the end, what we find is for the analysis that do not have background constraints, so NICER only consistent geometry for both data sets. And we can also use it as we did for J0740, also XLM, unpulsed data coming from the MOS detectors. And we can see that we end up with very different geometry and very different mass and radius as well. But this is not to be worried about because we know that this is probably missing further constraint on the background. So it would still working on providence and put it like that. Quickly going on J0740. So from Riley et al. 2021, we saw that this could be a model, the data could be modeled with SU, a model so two single temperature circular hotspots independent from each other. And the radius that came out was around 12.4 kilometers. The mass was already previously constrained. And so here I'm reporting again the posteriors, 1D posteriors, and the 2D posterior probability for radius, mass, and compactness. And this is actually work done by my colleague Tom Salvi. And what is the problem? The worry here is that for ending up, the result that we said it was upfront was the joint analysis with Accelera. And there is uncertainty of the cross calibration, and in particular the fact that we don't model the energy dependence of this cross calibration. So the question, this is why we like to have a nicer background constraint instead. And now what we can do here, so I added just two buttons. So now if you also look at the blue and red light curves here, you can see what's the effect of adding the space where the lower limit of the noise to background. And you can see that it's pretty consistent, and actually it makes sense in terms of logic on why it moves the radius similarly to what was done from the adding X and M. So divinity, the background. So on the lower limit, this that has some consequences on the compactness. This substantial, because the mass has been already fixed, and so this has a cascade consequence, which means substantially that we end up having larger radii compared to without any background constraint. And now here, what's the problem is that there is an AGI in the field of view also there. Sorry for skipping, I'm just trying to go quicker. So we can't really put properly upper limit, but so it's better to be cautious and only look at lower limit. However, we do also want to test the effect of upper limit, and we actually see some consistency in the logic that it goes. So again, putting lower limit makes radius larger because you will need lower compactness, because part of the impulse components is compensated by the background, and vice versa if you put upper limit. And here are these corners are nicer only and nicer and XNMM, and you see they are pretty consistent. And actually, this seems to, at least for this pulsar, it looks like the cross calibration does not seem to be a problem. And finally, as a last point for J0740, we explore antipolarity, and it is clear that we need quite an antipolarity, a strong antipolarity constraint. So we know that it has to be 25 degrees with 84% probability away from antipolarity. And so summary for this source is that we find almost all consistent results with what was in relativistic, except for a few that we know parameters that are explained by the different data. We don't need, so it's not needed to revise the analysis for the equation of state, and we see that the background is actually helpful also for reducing the credible interval. Again, no cross-calibration problem with X and M, but there's no evidence for that, and this clear antipodal construction. What next? Where we are working on different sources, and I will just very quickly go through this. And at the same time, so J0437, J0740, and J0030. And at the same time, we are also developing our pipeline, and we do want to, with further tools, and we also do want to have more simulations to test our analysis better. And with this, I'll end up with my conclusion, where I just leave you to read if you want this. But I do want to just stress that it is really, the message should be that we really need theoretical constraint and observational constraint to actually have a bit under control what's happening in our analysis. And with this, thank you for your attention.